In this video, I'm going to show you how to apply the work formula for a few examples. When we have an object and there are forces acting on the object, every single one of those forces does work on the object. Okay, we say that each force does work on the object, and the amount of work it does is calculated by the formula work equals force dot product with the displacement. And the dot product can be rewritten as the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them when drawn tail to tail. This was the previous lesson. So I'm going to try to apply this to a few examples. I did one example in the previous lesson, so here's more. The free body diagram for a 15 kilogram object is shown. If the object begins at rest, how much work does each force do on the object in 5.0 seconds? All right, so the question is asking us for how much work does each force do on the object in 5 seconds? So it's since there's 4 forces acting on the object, as shown in the free body diagram, this question is asking us for 4 different answers. Okay, one answer for each force. So the answer for 2 of those is actually going to be really quick. So I'm thinking about the gravity and the normal force. So the object moves towards the right. Okay, because gravity and normal cancel out, we have 50 newtons of applied force to the right and 20 newtons of friction resisting that to the left. So the velocity of this object, or the acceleration, but also the velocity, is going to point towards the right. So since gravity is straight down, gravity is at a 90-degree angle to the motion, to the velocity. So it's going to do 0 work because it's perpendicular. And same with the normal force. The normal force is pointing straight up, which is also 90 degrees to the motion of the object. So whenever the force is perpendicular to the motion, then the work is going to be 0. So force of gravity and normal force do 0 joules of work on the box. I'll say because they are perpendicular to the motion. All right, so there's one, or 2 actually, 2 answers. Now I'm going to focus on the applied force and friction. So applied force is in the same direction of the motion. So that's going to result in a positive amount of work. And friction's going on the exact opposite direction of the motion. So that's going to result in a negative amount of work. But to calculate the actual values, I want to apply the formula work equals force dot displacement, which means I actually need the displacement. Okay, I'm going to have to figure out this displacement before I can figure out the work. So I'm going to just write a little heading here. Just find the displacement. So I'm actually throwing in some math and ideas from units 1 and 2, just to keep you sharp. So for finding the displacement, the object starts at rest. V1 is 0 meters per second. The time that they ask you to do this for is 5 seconds. And the acceleration is going to be calculated with net force over the mass. That's Newton's second law. Remember, keeping you sharp here. And the net force, just looking at the free body diagram, the net force is going to be 50 minus 20, which is 30 newtons. And then the mass is given as 15 kilograms. So the acceleration is 2 meters per second squared. And I can find the displacement with one of the uniform acceleration formulas. You want to look on your formula sheet. It's going to be the third one. Where V1 is 0, so I can cross out the first term there. And now fill in the values to get displacement. And the 1/2 times 2 works out nicely. That just equals to 1. And multiply that to 5 squared, and that gives you 25 meters. So that's the displacement. It's to the right. Okay, so now that I know the displacement, I can go on and figure out the work done by the applied force and by friction. So I'm just going to write W sub A to stand for the work done by the applied force. So it's going to be the magnitude of the applied force times the magnitude of the displacement times cosine of the angle between the applied force and the displacement. So that angle is 0 degrees. That angle is 0 degrees because the applied force is to the right and the displacement is to the right. So there's 0 degrees between those directions. So this is going to be 50 newtons times 25 meters times cosine of 0 degrees. And the cosine of 0 degrees equals to 1. The cosine of 0 degrees equals to 1. So the answer is going to be 50 times 25 times 1, which is 1,250 to 2 sig figs. And the units of measurement for work are joules. So that's the work done by the applied force. And now finally the work done by friction, which I'll denote as W subscript F. We do the same thing, except we use the force of friction instead. Displacement's the same, cosine of theta. Now, what's the angle between the force of friction and the motion of the object? So the force of friction is to the left. The velocity is to the right. So they're in completely opposite directions to each other. If I draw them out tail to tail, one's to the left, the other's to the right. It's a 180-degree angle between them. So theta is going to be 180 degrees in this case. So I'll fill in the values. The magnitude of friction is 20 newtons. The displacement is 25 newtons. And this cosine of 180 degrees. Now the cosine of 180 degrees is exactly equal to -1. Cosine of 180 degrees equals to -1. So I'm really just doing 20 times 25 times -1, which is -500. The units are joules. Underline 2 sig figs. All right, so there's example 1. So in example 1, we had an angle of 90 degrees. That's the normal force in gravity, so 90 degrees to the motion. That makes 0 joules of work. We had an angle of 0 degrees. The applied force is in the same direction as the motion. and that gave us a positive amount of work. And for friction, the angle is 180 degrees. It's in the direct opposite direction of the motion, and that gives you a negative answer for work. Next question. A 5 kilogram box slides 4 meters down a ramp inclined at 30 degrees. How much work does gravity do on the box? And what about the normal force? So I'm going to add some details to the diagram here. The ramp is inclined at 30 degrees. So that's 30 degrees from the horizontal. And it slides a displacement of 4 meters. So I'll add that to the diagram. So the motion, I'll just draw an arrowhead there. The motion is down the ramp. That's which way the box is moving. Now I'm going to focus on gravity. Gravity, so the work done by gravity, W subscript G, I'll call it, using the formula for work, will be the force of gravity, magnitude, times the magnitude of the displacement, times the cosine of the angle between the force of gravity and displacement. So to figure out the angle, I'm going to be a bit more careful here. I'm going to draw a diagram. So I'm going to draw the two vectors tail to tail. So gravity is straight down. That's the direction of the force of gravity. Whereas the displacement is down the ramp. So there's the direction of displacement. So the theta for gravity is whatever angle is in between those two. What angle is in between those two? Well, going back up to the diagram, I see that I actually have a right angle triangle with 30 degrees labeled at the base there, which means that this angle at the top is 180 degrees minus 90 degrees minus 30 degrees, and that's 60 degrees. So the theta I use here is actually 60 degrees. So that's a bit of a trickier one. But otherwise, the rest of the answer is straightforward. I just fill in the values. So the force of gravity, actually one more step, the force of gravity is mg. That's the formula from last unit. So just make that replacement first. Force of gravity is mg. Now I'll fill in the values. 5 kilograms, 9.8 newtons per kilogram, displacement of 4 meters, cosine of 60 degrees. The cosine of 60 degrees is exactly 1/2, so that makes the math okay. I'm going to do 5 times 4 first. 5 times 4 is 20, times the cosine is 60, so 20 times 1/2 is 10. And then 10 times 9.8 is 98 joules. So that's the work done by gravity. And the normal force, well, in this case, the normal force, which direction does it point? It points perpendicular to the ramp, which also happens to be perpendicular to the motion. So the work done by normal is 0. Actually, you know what? I'll write out the formula. The work done by the normal is the magnitude of the normal times the displacement times the cosine of the angle between the normal force and the motion. But that angle is 90 degrees. And cosine of 90 degrees is 0. So 0 times whatever is going to give me an answer of 0. Okay, so that's why any time the force is 90 degrees to the motion, The answer is going to be 0 joules. Last one. An elevator moves a 70 kilogram man up 12 meters at a constant velocity. Determine the work done on the man by gravity, and how about the normal force? First thing to realize is that since this is going at a constant velocity, the forces are equal. All right, and that's actually going to help me save a little bit of time if I realize that they're equal. So I'm going to start with gravity. The work done by gravity, write out the formula first. It's the force of gravity times the displacement times cosine of the angle between them. Now what's the angle here? Well, which way is the force of gravity? The force of gravity is down. And which way is the motion? The motion is up. So if I draw those tail to tail, what's the angle between them? They're directly opposite to each other, so it's 180 degrees. So with this formula, I will do mg for gravity times the displacement times cosine of 180 degrees, which equals to -1. So it's going to be the mass, 70, g is 9.8, the displacement's given as 12, cosine of 180 is -1. And we'll multiply all that out together. I'm not going to finish this off with the calculator. I don't have one on me, but the answer is going to be negative something or other. Okay, joules. Actually, I will do it. Just give me a second. All right, negative 8,232 joules. Now the work done by the normal force. Now, what's the only difference between gravity and normal? Because they're the same size. Okay, they're the same size. So when I write out the formula, the magnitude of the normal force is the same number as the magnitude of gravity. So everything's the same except for the direction, or theta. Okay, so for the normal force, normal force points straight up. And the object is also moving straight up. So what's the angle between those two arrows? Well, it's 0 degrees. So the only difference between the previous question for gravity and this one for normal is that instead of cos 180, we're doing cosine of 0. And the cosine of 0 is just +1. So in all the math is the same, except instead of the -1, it's a +1, which means the answer is just going to be a positive 8,232 joules. All right, so those are some examples for you, and I'll get you guys to try some, and you can submit them to the hand-in folder and get some feedback.